This week, the topics of our mini lectures are going to be rotational motion and gravitational forces. And we'll see how rotation and gravitation work together in order to explain a lot of the beautiful things that we see in our universe. Before we dig into the topic, first we are going to introduce a few definitions that we need to understand rotational motion, and we will see these again later on in different parts of our semester. Okay, so here we have a circle, and we are going to pass through on our journey around this circle some angle theta. Okay, and this change in angle that we make as we move from point A to point B here, that change in angle we will identify as delta theta. That equals to the change in arc length, S is the arc length, divided by the radius of that circular path. So if we come over here and look at our circle, delta theta here, that's the angle that we move through to move from points A to B. Okay. And S is what we define as the arc length. It's the distance along that path, along the edge of the circle, along the circumference of the circle. The delta just means the change in position along the circle. R, again, is the radius of your circle. So if we have this relationship, delta theta equals delta S over R, we can rearrange it. And we can say that the arc length that you pass through this distance along the edge of the circle, that distance that you pass through is equal to the radius of the circle times the angle that you traversed during your path from A to B. Okay, so this is important. I know that so far in this class, we've been working with our angles in units of degrees, but here, an arc length is a unit of distance. The rotation angle is given in units of radians. Okay, so keep that in mind. If you are using the equations like this, we want to think about our angle rather instead of being a degree as in units of radians in order to get the right units on our answers. Okay, so to remind yourself about the relationship between an angle in degree and an angle in radian, over here, 30 degrees is the same thing as pi over 6 radian. 60 degrees is pi over 3 radian, 90 degrees, pi over 2, 120 is 2 pi over 3, 135, etc. 360 is 2 pi, 180 degrees is pi. Say we want to convert from our angles in degrees to our angle in radian. How can we do that? Well, if we are given an angle of 30 degrees, we got to get it in radian. I always know that 180 degrees is the same thing as pi radians. So I can multiply my 30 degrees by a conversion factor. If you take your angle in degrees and you multiply it by the conversion factor that says there's pi radians divided by 180 degrees, then you'll be able to put your angle in degree into angle of radian. So if you ever need to change from degrees to radians, you can take your angle in degree and multiply it by pi radian over 180 degrees. That's our conversion factor, and then that will give you your answer for the angle in radian. Or you can just convert it on your calculator. Okay, so we are going to be using a quantity that we call the angular velocity. We're going to use it a little bit here, the angular velocity. The angular velocity is similar to the linear velocity. That's the velocity that we've been using the whole time up until now. Angular velocity we're going to represent as the little Greek letter omega, which is just this curly W. Angular velocity is the change in angle per unit time. So angular velocity is equal to our change in angle, this has to be in radians, divided by our change in time. So the unit for an angular velocity is radians per second. Radians per second, not a degree per second, it's radians per second. So this, again, this angle has to be in units of radians. And there's a conversion between linear velocity and our angular velocity. So linear velocity is equal to the change in your arc length over change in time, because a velocity is a distance over time, an arc length is a distance. So the distance that you move through along the edge of your circle here, that's our arc length, delta S over t. And in the previous slide, we showed that our arc length is the same thing as the radius times your change in angle in radian. So you could also say that linear velocity is equal to delta S over delta t. It's also equal to r delta theta over delta t. And so we have the relationship then. Oh, and in this equation here, we've got r. We just showed that delta theta over delta t is omega, our angular velocity. So then we can say that our linear velocity is equal to your angular velocity times the radius of the circle. Or we could rearrange this and show that the angular velocity is equal to the linear velocity divided by the radius of the circle. Okay, so let's check to see how well you're understanding this topic. Linear velocity is the instantaneous distance over time quantity of a point moving around a circle. Okay. Linear velocity has the same magnitude but is constantly changing in direction as you go around a circle. So here I have a fly on the edge of a record player, okay? And then that fly here has its velocity vector, its linear velocity vector, always tangent to the edge of the circular path, okay? So the magnitude of that linear velocity is always the same, but you see that this vector is always changing position. So whenever the fly is down here, the vector is pointing off in this direction, tangent to the edge of the circle. So our magnitude is always the same, but the direction is constantly changing, okay? And as you're executing this linear velocity, your arc length over time, your arc length is your distance along the path, you're also moving through some angle theta, through some angle of part of the circle. So if we went from up here to down here, we are moving through 90 degrees or pi over 2 radians as we did this, okay? So we're going to check to see how well we've understood this topic with this question for the engagement check. Let's say we have a ladybug and it's on a rotating disc and it's moving through an angle theta at a distance here of r1 from the center of a disc. And we have a beetle that moves through this same angle, delta theta, at a distance of r2 from the center in the same period of time. So the ladybug moved from here to here, the beetle moved from here to here. Okay, they're moving through the same angle of the circle, but you see that the beetle had to move through a larger arc length as compared to the ladybug, which was moving through a shorter arc length. So with this information and talking about our definitions of linear velocity and angular velocity, which bug is going to have the greatest angular velocity? The ladybug or the beetle? Which bug has the greatest linear velocity? The ladybug or the beetle? Now, sometimes when we're talking about angular velocities, we will use different units. So you could report an angular velocity. Remember, angular velocity is equal to our change in angle over our change in time. Okay, so you can report your angular velocity in units of radians per second, or sometimes we use revolutions per minute. Okay, so what's a revolution? So one revolution is the time it takes you to go, or sorry, one revolution is the distance it takes you to go all the way around the circle. Okay, so let's say we're given something in radians. Let's say I have an angular speed or angular velocity of 50 radians per second. And I want to put it into revolutions per minute. Okay, so I know that there's 60 seconds in 1 minute. Okay, so that's my conversion factor. And I know that in 2 pi radian, that's 1 revolution around a circle. So a revolution is 1 complete path around your circle. So 1 revolution is the same thing as 2 pi radian. So my units of radians cancel here. And so if I take 50 times 60 and divide it by 2 pi, that will give me my angular velocity in terms of revolutions per minute. Then this answer would be 4.77 times 10 to the 2 revolutions per minute. Okay, and then so that's also 477 revolutions per minute. So sometimes I might give you an angular speed and revolutions per minute and revolutions per hour, and maybe you want to know that in radians per second or some other unit. So that's how you can convert, for instance, between radians per second and revolutions per minute. Now let's talk about something called centripetal acceleration. Centripetal acceleration is the change of velocity of an object associated with uniform circular motion. Centripetal, the word centripetal means center seeking. The direction of the centripetal acceleration is always toward the center of curvature of your path. Okay, so here we have an object that is executing circular motion. That means that the centripetal acceleration vector will always be directed toward the center of the circular path. Now, you can think about centripetal acceleration as the change in a linear velocity over a change in time. Okay, so over here, I've got my object is moving along this arc length delta S. At this point right here, it has a velocity vector. At this point over here, the velocity vector has changed. The magnitude of that velocity is the same, but the direction of the velocity changes. So the centripetal acceleration is the change in this linear velocity over the change in time. So the change in velocity always points toward our center of curvature of our circle. So as you move through an angle theta, like we do in this figure here, move through some angle theta, the magnitude of the linear velocity stays the same, but yes, the direction changes. Now, so we can write centripetal acceleration like this, the change in the linear velocity over the change in time, or there's a couple of different ways we can write it. The centripetal acceleration is equal to the linear velocity squared over the radius of curvature, or the radius of the circle. And this is also the same thing as saying that the centripetal acceleration is equal to omega squared times r. So you can say both of those things. And on your equation sheet, you have a whole section that says chapter 6, circular motion, and the angular velocity is given there, the linear velocity. The centripetal acceleration is also shown in these two forms right here. Okay, so you have that for you always when you're working through problems. Some problems, it might be more advantageous to use the centripetal acceleration is equal to v squared over r. Sometimes it's more advantageous to use centripetal acceleration is equal to your angular velocity squared times r. Our linear velocity is always tangent to the edge of the circle, but our centripetal acceleration is always pointing toward the center of the circle. Okay, so let's think about this then. We have a coin that's rotating on a turntable. Here's my coin, and it's sitting on the turntable. The turntable's moving. The coin has enough friction between it and the turntable that it doesn't slide. So it moves without sliding around this turntable. At the instant shown right here in this figure, which arrow gives you the direction of the coin's velocity? So we already said that the linear velocity is always going to be tangent to the edge of the circle, and at that instantaneous point is going to be pointing tangent to the edge of the circle in the direction of motion. So A right here is going to be the direction of the coin's velocity when it's sitting right here. Okay. Now, the coin is still on the turntable, but at this very instant, imagine the frictional force disappeared. The frictional force was what was keeping that coin from flying off. Okay, imagine that we suddenly turned off friction. We were in a perfectly frictionless world. In which direction would the coin move? It would also continue to move on in the direction of the velocity vector. If we suddenly turn off friction, there's nothing to keep that coin continuing around the circle, and it's just going to move off in the direction of its linear velocity at that very instant. So if we suddenly turned off friction, then this coin would go flying off in this direction, and it would continue without stopping until it encounters another force or another object to stop it. Now we're going to apply these ideas of centripetal acceleration and angular velocity to solve this problem. I'm not doing it on the whiteboard because this is a pretty simple problem. I'm going to do it real quick here on my iPad. We have a race car that accelerates uniformly from a linear speed of 40 meters per second, that's our initial velocity, to a speed of 60 meters per second in 5 seconds. T is equal to 5 seconds. While traveling around a circular track of radius 400 meters. When the car reaches a speed of 50 meters per second, find the magnitude of the car's centripetal acceleration and the car's angular speed. Remember that centripetal acceleration is equal to v squared over r, but it's also equal to omega squared r. Well, in this problem, we're already given the velocity, linear velocity, that's what the v is here, and we're given the radius of the circle. So we can just use the first way we could write centripetal acceleration. So we can use the v squared over r here, not the omega squared r in this case. And so we're just asked to find the magnitude of the centripetal acceleration when the car reaches 50 meters per second. Okay, so that's easy. The centripetal acceleration is just going to be 50 meters per second squared divided by the radius of our circular path, which is 400 meters. So the centripetal acceleration, which has units still of meters over second squared, is going to equal 6.25 meters over second squared, okay? And then for part B, the car's angular speed at the instant when it has a linear velocity of 50 meters per second, well, we can use our equation for angular speed, which says that, well, on your equation sheet, we've got the linear speed equals omega times r. So if we solve that for angular speed, omega is equal to v over r. And so at the instant when we reach 50 meters per second, we divide that by the radius of our turn, 400 meters. So the angular speed here is 0.125, and the units are radians per second. You see that there's a meter here on top and a meter on the bottom, which cancel. So the units for our angular speed are going to be units of radians over seconds.